Welcome back for another presentation from RSLogix 5000 course. If you've not realized it yet, I'm sure it's soon going to occur to you that I cover a lot more material in these lectures than is in the manual. My goal is not to go over everything that's in the manual verbatim, but to generally kind of elucidate or what's a better word, to expand on the general principles that are in these lab projects. All of the lab projects are designed to demonstrate very important characteristics of the behavior of these processors. I say processors because we're really not to controllers yet. A controller has a processor, power supply, and I/O. So far, we're just dealing with pretty much the processor and the memory aside from I/O, even though we did demonstrate some I/O items, we threw a couple rungs of logic in there. So the previous lecture to this was first bits, where we actually worked with a couple of bits, my first bit, my second bit. We gave them ridiculous names just to clarify the point that a bit is a bit, and it doesn't matter what you name it. You could call it monkey shines, dingleberries, whatever you want to call it, it doesn't matter. A bit is a bit. In this presentation, we're going to expand it to rungs of logic. And the last lecture and lab project is extremely important for you to get, I guess, an intimate relationship with the data table, with memory, and how things function in memory, and the fact that you can do whatever you want right from your keyboard and mouse. You can go in and turn things on and off. In this one, we're going to do rungs of logic. Now, when you are influencing the state of bits or the value of words in memory from your keyboard and mouse, that's external. When you write a rung of logic, it influences the state of bits in memory. That's not external, that's internal. You wrote a program and said, if this and this, then do that. And you download it into the controller. Now you have two things that influence the state of bits in memory. The last lecture was from your keyboard and mouse. With this one, it's going to be rungs of logic. So now you're adding rungs of logic that are influencing the state of bits in memory. And like I said, I always try to go over more than what was in the manual and do a mind dump on you. Let's do this. We are at approximately page 95 in the manual, plus or minus a page. Your first run of logic using I/O controlled bits. What we have in front of us is the project that we left with at the end of the Just for Fun session that we had, and these are all internal bits. My second bit, my first bit, those are just bits in memory. The fact that they're Boolean, see, data type bool, that doesn't mean that it's an isolated bit somewhere in memory. It's actually using a double integer. This tag, whenever you create a bool type tag, you're using one bit of a 32-bit dent. So you just took up 32 bits of memory when you create a bool. Now if you've got plenty of memory, don't worry about it. By all means use bool data types. But remember, we could have used a dent data type. We could have used a dent data type instead of a Boolean, and then use one bit of that dent for each of these tags. We're going to continue with this logic, but we're going to alter it, change the function a little bit. Remember that the scan dependent logic that you see in front of you had erratic behavior, and that is it constantly cycled every other program scan. So every 20 microseconds or so, it would flip state on its own simply because it's scan dependent logic. And the idea of just for fun was this is not something that you want to do, but you need to understand the nature of the scan of programmable controllers. Last man wins. Let's move on here and start editing this code. First thing we're going to do is we're going to click on that to open it. We could type in the first two letters. We have type forward. So L brings us nothing, but O brings us into the tags that begin with local. And the reason we do that is if we just open up this, then we have to drag down, and as this list gets longer, the tags that begin with local get deeper and deeper into the list and become troublesome because you have to scroll down. However, we typed in local and it came up C, but we want an input, data, and pick bit 0. Now this is a module defined tag. This directly is the bit in memory that is controlled by the input field device. And then we want this instruction to have the same tag, meaning that both of these instructions are going to address the same bit in memory. This is a true if off and a true if on. In the manual we also showed you some other possibilities of using substitute tags. We're not going to do that here. We're going to stick to the tags that we actually have with the controller that we have. It's up to you to make that correlation between the tags we're using and the ones that you're using if you have different hardware. But we gave you the examples so you could make the transition yourself. Make sure all of your input devices are off, and then open the watch panel. Remember, view, watch. Drag this up a little bit so you can see these two tags. Remember, we're offline right now, so in the manual I had you download and go online. Select the processor, download. Notice that down below here we had the watch panel open, but it reverted to errors. This always happens when you download. Complete, 0 errors, 0 warning. Even though there's no errors, no warnings, it still pops up. You can click on watch to go back to the watch panel. Okay, now we're downloaded and you were told to be in the run mode with both bits off. Well, if you look down there, you can see that my first bit is on and my second bit is off. One of these is going to be on and the other off. Even though you turn them both off, and we can turn this one off again. However, because both these instructions address the same bit in memory, this one is true if off and this one's true if on. If this one's true if off, then it turns on my first bit. One of these two bits is going to be on because one of these two instructions will always be true. If the bit is off, which it is now, or if the bit is on, then this will be true and it'll turn on my second bit. Why is the state of my first bit on or 1? I just explained that because local 1 I data 0 is off. The instruction is true if off, therefore it turns on my first bit. How many bits are we looking at in this example? Well, we're looking at 3 bits. We're looking at local 1i data dot 0, even though it's shown in 2 places, that is just 1 bit. And we know the state of it by looking at it because the true if off instruction is true. It's marked true. That's what the highlighting is here. Remember, these are true or false, these are on or off. So we're looking at this bit, my first bit, my second bit. Those are 3 separate memory locations. Are any of the inputs on? Meaning, are any of the input field devices on? No, they shouldn't be. We said to turn them all off. We haven't turned any on. Are either of the rungs true? Yes, the first rung is true. If there are any true rungs, which instructions are true? This instruction right here, and I always call this true if off. True if that bit in memory is off. True if that bit in memory is on, even though Rockwell and Allen Bradley have different names, XIC and XIO, I think it's easier to say true if off or true if on. How can you discern if an instruction is true? Because it'll be highlighted. even if we go and change the color, and I believe we can do that under options, font color, and I can go change the power flow to, well, actually I like that cyan. We'll make it a lighter, something lighter. Okay, so now you see it bumped us back and knocked out our geyser button. So let me pump that back up in size. Is the bit, my first bit, true? No, it's not true. Bits are never true. Instructions are true or false. Bits are on or off. My first bit is not true. Change the position of the switch attached to the screw terminal on your input module that directly influences bit 0 of the input module, or in our example, local 1i data.0. Now you see this instruction is true because that bit is on in memory. One more time, if you didn't see how I changed those colors, you go to Tools, Options, Ladder Editor, Display and Font Color. Then we go to Power Flow. I like that color better. You can change all the colors on your window here, most of them anyway, but remember, less is more. The less you have to distract you, the more you can see what's going on. So less is always more. Now we could also have used N00 here. So I'm going to double click to put this rung in the edit mode. I'm jumping ahead here now. I don't think I had you do this in the book, but I can go in and put in IN00, hit enter, finalize all edits, and it is still the exact same logic because input 00 points to local 1i data.0. So these two have the same base tag, or rather, if you wanted to say this is the base tag and this one points to the base tag. Here's what I wanted to point out. N00 is alias to that bit in memory, but that bit in memory is not aliased to IN00. I can create as many tags as I want alias to that module defined bit in the data word. And whatever one I happen to put in, that's the one that will appear. So you could see two different tags here, IN00 and something that we didn't create, but we said we could, both alias to bit 0 of that input card. It's the base tag that matters, not the tag that it's aliased with. If we go back to our watch window, you see this is our bit right here that we are changing. Local 1i data, that's bit 0. I'm going to change this back just to make sure it matches what's, well, I didn't mean to do that. Then I can drag this up there, finalize all edits, and we're back to where we were in the manual. And in the manual, I ask you, why is the instruction in rung number 0 false, and why is the instruction in rung number 1 true? This instruction is false because that bit is off in memory, true if off. This is true if on. This instruction is true as indicated by the highlight because that bit in memory, that location that this instruction addresses, that bit is on. Can both rungs ever be true simultaneously? No, because one of these instructions will always be false because that bit can't be in two states simultaneously. Can a true if on and a true if off both be true simultaneously in the case like this where they are both querying, addressing the same bit in memory? The answer is no. Consider the above rung of logic. There is a switch attached to the screw terminal labeled input 0. Is that switch open or closed at this moment? Now, That's kind of a trick question. It wasn't intended to be a trick question, but that switch is a toggle switch. If you were told to turn it on, then it is switched closed at this moment. Is that bit 0, on or off at this moment? That bit is on. Answering the last two questions correctly is a good indication of your passing the single largest barrier to transitioning from relay logic to ladder logic diagrams. And that is disassociating what the field device is to the symbols in the logic that resemble possibly field devices, like field devices that have normally open and normally closed contacts. So let's consider this rung right here, rung 1. There is a switch attached to the screw terminal labeled input 0. Are those switch contacts open or closed at this moment? They're closed. Is that bit on or off? It's on. Now that we've worked with some actual inputs to control logic, let's turn our attention to outputs. And this is approximately page 100 or so in your manual. We had you go offline with your project. It's always good to save first. And I have mine saved 2 rungs with input. So I'm going to say File, Save As, and then I'm going to change input to in out. Not really that clever, but enough to remind me of where I was at when I saved it. Okay, go offline with your project, and we're going to change the tag, my first bit. We saved it, go offline. We go to my first bit, double click, type in LO, drop down, and we want an output from the module in slot 1. So we want to open the data and assign it bit 0. Now we have both an input field device and output device in rung 0. We also could have used OUT00. We could have used the looks like tag, local _1 _0 data dot 0. But we're going to use the direct module defined tags that we have with our module. Now for my second bit, we're going to do the same thing. Double click, drop down, and make that bit 1. Now before I do that, well, I'm going to go ahead and do that. Okay, and you see that's what you did in the manual. However, I could have done this. I could have dragged that down here to the green Mimi, double clicked, click behind the 0, backspace 1, enter, and accomplish the exact same thing. Remember, this is just text. If you double click on the head of this rung, here's the ASCII representation of that rung. XIC, true if on, local, notice there's an open parentheses, local :1 :I dot data dot 0, close parentheses, OTE, which is this instruction, and then the memory location that is addressed by this instruction. So it's just text. When you save it, it's just text. You don't save it as symbols. However, RSLogix 5000 interprets that string of text as this graphical representation. And I had you save the project as beginner L, whatever your processor number was, 2 rungs in, out, download, and go online in the run mode, all devices off. So make sure that you turn your input back off that you had on. So communications, Who active, pick your processor, download, waiting, and still waiting. Remember, this is RS-232, 38.4K baud rate. Sounds fast, but compared to Ethernet 100 meg, this is really slow. Change back to the remote run mode. Here we are with the inputs off, and we're back in run mode. How many bits are we watching in the watch panel? Well, let's go to the watch panel and find out. View, watch. Well, here I see 3 bits, 1 input and 2 output. It's showing it as words and it's showing that bit 0 is on, this bit right here. But we have 3 bits. We're watching input bit 0, output bit 0, output bit 1. So we're watching 3 bits. Which of the 24 bits displayed are we watching? See, there's 24 down here. Okay, so we're watching bit 0 right here, this one. We're watching the first 2 here, 0 and 1. Now it shows it twice because it's used here twice. Toggle the switch to input 0 to the on position while watching both the rung of the logic and the appropriate bits in the watch panel down here below. We're going to switch on that input right there. So watch here and up here when we do that. Now notice that we have a different bit on here in the output word and we have an input bit on. So that was true if off, and it was true and output 0 was on. But when we flip this on, this is now false, which turns that off. This is now true, which turns that on. And if you have a digital field device simulator, you were working with the top switch, input 0. If I flip it off, then the red light on top is on. You know, if I flip it off, the red light is on. If I flip it on, green. If I flip the switch up, it's on, the green light is on. If I flip the switch down, it's off, and the red light is on. So on my digital field device simulator, if the toggle switch is down, the red light is on. If the toggle switch is up, the green light's on. And if you have that simulator, then you're seeing the exact same thing. Toggle the switch to the on while watching both the rung and logic and the appropriate bits in the watch panel below the logic panel, which is right here. If you're using tags in 0, out 0, and out 1, then you're going to see something different down here in the watch panel. But if you're using the tags that we're using, then you're seeing what we saw right here. In other words, this could have been in 0, 0 and out 0, 0, out 0, 1. If you were using the substitute tags. We're going to do this next edit online. We're going to double click to select and edit this rung. Rung number 1, double click to edit it. Mouse over, hold down the left mouse key over this bit right here. So now you've got it in trail, and drag it over until the tag Mimi is green, and then release it. So we're going to drag it over to here, finalize all edits. After you finalize, and by the way, notice that you have a warning. You do have a warning. Warning, duplicate destructive bit reference, local 1, O for output data, bit 0. And you should never address the same bit in memory with 2 OTEs. Now we did this on purpose to demonstrate why. After you finalize all edits, when you go into the run mode, and before I click on yes, you will notice a peculiar behavior with the actual output device. The LED associated with this memory location, local :1, slot 1, O for output, dot for data word, dot 0 for bit 0 of that data word, will intermittently energize when it should be de-energized, and de-energize when it should be energized. A momentary flickering of the output LED and the device connected to that output. For now, ignore this. We will explain it. We're doing this on purpose. It has something to do with that destructive bit that you see down below in the warning. Duplicate destructive bit reference detected. And the age-old philosophy of last man wins when it comes to ladder logic, when it comes to sequential code. Yes, to finalize, put it in the remote run mode. May or may not be able to hear my outputs flickering in the background. Now I do want to say something else. Depending upon how you left your program, because remember we were addressing output 0 and 1. This was addressed to output 1. So right now if you open up controller tags and go to, you'll see local 1O data, you'll see that there are 2 on. Well, we're only turning 1 on. We're only controlling one of them. So this one is what I call data table carnage. It was left on by the previous program. In other words, the last thing that bit heard from the program was that you're on. And then we edited the program, and we never went back and executed a false execution on that OTE to tell it was off. Pay particular attention to this when you're doing the labs, because you may accidentally leave a bit on. Maybe in the manual I should have said to turn it off. That's just one of those little oversights. Anyway, pay close attention to that. You may not have noticed in the just for fun, but when we finalized all edits, a message appeared in the errors box, just as we see down here. This box is your buddy. Always pay attention to this. If it says 0 errors, 0 warnings, as you can see, that doesn't really mean that there's no warnings of any kind. But if it says 0 errors, it's going to let you run the program. Often I have warnings because I tend to stretch things in unconventional ways, and it works perfectly fine. They don't disallow you from being creative in how you write your code, but they can come up and warn you about something that you have done. Remember that RSLogix 5000 is not smart enough to really analyze what you've done. It can only look for certain structures that it has deemed as not a good idea. That doesn't mean you can't use them. Here I have 0 errors, 0 warnings, but I do have a warning that I have a destructive bit, meaning that I've assigned 2 unique OTE instructions to exercise the same bit in memory. Well, now let's go back and look at our logic. So I can just hit this X here to get rid of that image, because this is what we need down here. As long as we can see this, we're looking at the data table here, and we're looking at the code here. Are both rungs true? No, they're not true, because this has a false rung out. This has a true rung out. So this rung is true, this rung is false. However, if you were to get tangled into looking at these instructions, and because they're highlighted saying that the rung is true or that they're true, you would be mistaken. Whenever you see an output type instruction, any instruction that executes against a bit in memory, not reads a bit in memory like these over here, but executes against it, this highlight means that that bit in memory is on, not that the rung is true, and not that the instruction is true. This instruction is never true. It is only on or off. And you can see here that this rung is not true, and yet that's highlighted. It's highlighted because that bit is on in memory, not because this rung is true. Presently, the switch attached to input 0 is in the on position, contacts closed, completed circuit. And if the controller is in the remote run or run mode, then that bit is on in memory, and the first rung is false, and the second rung is true. Flip the switch to the off position, contacts open. Are both rungs true? No. Why is the output instruction in rung 1 not highlighted if the rung is true? Rung 0 is true. So if we read this logic, now remember that the order that a programmable controller does things in. Now the Logix engine is slightly different than the traditional controller scan. In the traditional controller scan, we'll leave out all the housekeeping stuff. We'll just talk about inputs, outputs, and the program execution. In a standard controller, the chipset goes out and collects the state of all the input devices and stores them in memory. Then the code, what you're looking at here, executes. After it's done, then it takes all the bits in memory, words in memory, associated with output cards, and sends them out over the back plane to those cards to control those outputs. So it's read the inputs, execute the code, and then refresh the state of the outputs. So we go read the input. This bit is off, as you can see here. This bit is off, so this rung is true. it says to memory, local 10 data 0, you are on. And then in the next rung, this instruction is false. So the false execution of this OTE says local 10 data 0, you are off. Then it updates the outputs. Now you would think, based on what I just described, that the output would be off because last man wins. In other words, two of you want something for lunch, and the person running to get it says, well, what do you want? And the first guy says, I want pizza, and the second guy says, I want Thai food. Well, guess what you're going to get? You're going to get Thai food. Last man wins. Now, the caveat here is that the Logix engine has a different structure in how it handles I/O. Remember the requested packet interval. You go down here to this module, double click to bring up the properties, or you could have right click properties, look at connection. It has a requested packet interval of 20 milliseconds. And we explain that that means aside from the processor's intervention, the memory locations in the controller's memory that represent the state of inputs and outputs are going to be refreshed every 20 milliseconds regardless of what the processor is doing. Now, in different hardware platforms like ControlLogix and CompactLogix, that's accomplished different in both cases. Nonetheless, in the traditional PLC, Programmable Logic Controller, you could depend on all the inputs being refreshed, then all the code executed, and then all the outputs refreshed. However, and that is synchronous. The functionality of updating memory from inputs, executing the code top down, left to right, and then updating and refreshing the outputs, that was synchronous. With the Logix engine, that's not true. We have a continuous task represented over here, the main task. See the little clockwise swirly? It's trying to execute all the time except for some background tasks having to do with data communications and maybe an HMI. But basically the main task, the continuous task in this case, is continuously executing. And the I/O is being maintained non-synchronous or asynchronous with that. That's why you're seeing this odd behavior of things flickering on and off. The code has not changed. Why would it show this off sometimes and on other times? I mean, if you look down here, you can see ones pop up once in a while. It seems to run in little short runs of it's on a lot or it's off a lot. Right now it's off a lot, but I did just see it flicker on. Now you'll never see this input flicker on because this input is off because it's off. This input is only controlled, this bit in memory, as long as the processor is powered up and not faulted. This bit is going to represent the state of that input regardless. However, this bit does not represent the state that the output is in. It represents the state you want it to be in. But it's only going to do that if it's in the run mode. And in this case, we have I/O getting updated in between rung 0 and rung 1. In order for this bit to be on, then after the scan of rung 0, the output gets updated and told that it's on, and then this rung gets executed and it's told it's off. But it doesn't tell it that it's off until next time around. And maybe it hits it just right, so it's updating the output right here. Execute rung 0, update outputs, execute rung 1, execute rung 0, update outputs, because it's every 20 microseconds. I hope you get that. And of course, we do have many ways to deal with this behavior. Well, one is you just don't use two OTEs to execute against the same bit in memory, to address the same memory location. Just for the fun of it, just for grins, as some say, let's point out that this logic is off most of the time. I mean, that bit is shown off most of the time. When I look over at my digital field device simulator, I don't see the light on very often. Every once in a while it flickers on, every once in a while you see this bit flicker on. Now just for grins, let's take and drag this rung, select this rung, and drag it down below that rung. In other words, flip the order that they're executed in. And go back to the watch. Now, what do you see different now than what you saw before we flipped the order that these two rungs are executed in? You see the bits on most of the time now, and every once in a while it might flicker off. There, it just flickered. Now I have a relay output card. Well, I have the IQ6XOW4, which is 6 solid state inputs and 4 relay outputs. When my outputs go on or off, I hear the noise from the relay contact. I don't have to see it flicker, I can hear it. Notice that last man wins most of the time. With the Logix engine, unless you go through some special efforts to prevent scan-dependent logic like this, there is a way to make this work. Either way, I would never use two OTEs executing against the same bit in memory. But we could buffer our I/O, and we'll discuss that in a later lab. That's in this volume. And you wouldn't see this intermittent behavior. Last man would always win. But when you have asynchronous I/O activity in memory, then the memory can get updated in between these two rungs.